The broadcast is now starting. All attendees are in listen-only mode.
So, hello everybody. Hopefully you can see my screen. I would like you to welcome to today's webinar from Keysoft on gear mesh and bearing characteristic frequencies. My name is Sebastian Matkovic. I am a software developer at Keysoft, and I also work as a part-time researcher in the University of Ljubljana on the Faculty of Mechanical Engineering, laboratory for tribology and gears. So in next 1 hour, we will cover the following 7 topics. Why are characteristic frequency important? Then we will look on how to calculate it and what are gear characteristic frequencies, followed by the rolling bearing characteristic frequencies. And then we'll also have an overview of other frequencies in the system. Next, I will show what is the importance of the characteristic frequency in the design phase, and also what is the importance of the characteristic frequencies in the predictive maintenance phase. And at the end, I will conclude with a short summary of today's presentation. Now, I don't know if you can hear the sound. Here's an electric motor, and I would like to play a bad sound, which is quite loud and a lot of harshness. And here's a good sound with lower noise and lower harshness. I had this slide because one of the important topic where the characteristic frequencies are important is noise, vibration, and harshness analysis. In this field, the characteristic frequencies have important role, and as we all know that noise, vibration, and harshness is important in today's EV drives, as there is no more masking sound from the combustion engine. Also, the noise, vibration, and harshness is important in other modern transmissions because a lot of users connect the failure of the transmission due to increase or change in noise, vibration, or harshness. The other important topic where the characteristic frequencies become very important is when we have already operational gearbox and we have some oscillometers or some other devices to capture the signals, and from these signals we can with certain analysis we can have the amplitude frequency spectrum, and there we can have the characteristic frequencies. So these characteristic frequencies are very important in the predictive maintenance, and with the predictive maintenance we can prevent the catastrophic failure, and this topic is important mostly in the industrial gearboxes and also wind turbines and so on. Now something general on the frequencies. So by definition, the frequency describes how often a particular event, phenomenon, or occurrence repeats within a specific period of time. Usually the main unit is hertz, so the number of cycles or some oscillations that occur in 1 second. Often the engineers are describing the characteristic frequencies in cycles per minute, so the number of cycles that occur in 1 minute, and usually they use the variation CPM and not RPM. The third important unit, let's say, is the order. So when we have one main frequency which divides all other frequencies in our model, and this we call the order analysis. So on this example, we can see that we have Fn, which would be the main frequency, and we would divide all the other frequencies with Fn, so that the first order or base frequency would be Fn, and Fx would be the 25th order of that frequency, and the second harmonic of Fx would be the fifth harmonic of fifth order of this Fn frequency. Now, in the literature and also when discussing with different engineers, we stumbled across that sometimes users use the base frequency, and then they have the harmonics, which are first harmonic is the second order of the base frequency, third harmonic is the third order of that frequency, and so on. And to avoid this usage in Keysoft, we have implemented that the base frequency is the first harmonic, and so the second harmonic would be 2 times the base frequency, the third harmonic would be 3 times the base frequency, and so on. Now we came to the gear characteristic frequencies and some basic theory why are they present in the system. So if two gears are meshing, we know that we have a change in contact ratio. So once one gear is in contact, then second gear is in contact, and so on. So we have some fluctuation in the stiffness of the gear pair. Now this fluctuation of the gear pair occurs with certain frequency, and this frequency is speed dependent. However, the frequency analysis doesn't say anything about the amplitude, and amplitude are the function of other parameters such as contact stiffness, damping, and so on. Frequency just says what is the occurrence of this event. Now here we have two images, the standard design and optimized design. In standard design, the contact ratio is below 2, and we can see really this difference in the contact stiffness. However, even if we have the optimized design, we still see some fluctuations on the line here. And this is the theoretical stiffness. But if we consider some manufacturing deviations or even transmission error, this fluctuation could be even higher. Therefore, the frequency analysis should be also done in the optimized gear design. And again, the characteristic frequencies are speed dependent. Therefore, they are depending on how fast the gears are rotating. Now, in the gear pairs or bevel gear pairs or cylindrical gear pairs, we can identify 5 fundamental frequencies. The first 2 frequencies comes from the shaft, so the shaft of the pinion, the shaft of the gear wheel, and then we have the gear mesh frequency, which is calculated by multiplying the number of teeth on that gear with the rotational frequency of the shaft on which the gear is mounted. Then we have also the Huntington frequency. The Huntington frequency is calculating by considering K, which stands for greatest common divisor of the number of teeth of both gears in contact. We can also identify an assembly phase frequency, which is calculated by dividing the gear mesh frequency with this greatest common divisor. And of course, all the mentioned frequencies can be modulated by the sidebands coming out from the shaft. Now, to easily imagine what the assembly phase frequency, I prepared a video where we have a pinion gear with 18 teeth and a gear wheel with 30 teeth. So both of the numbers can be divided by 6, therefore the greatest common divisor is 6. Now when this gear train is assembled, we can see that on this pinion we have one gear in contact with another one, here the second with another one, and so forth. And at the end we can see that only 3 gears on pinion are in contact with the 5 gears on the wheel. Therefore, from the assembly onwards, only these 3 or 5 teeth are in contact. Therefore, if we can imagine that on one tooth some damage would occur or some deviation, it would transmit only on those 5 teeth. Therefore, this can lead to higher risk of failure and uneven distribution and creating noise and vibration. Now, in the second example, we have assembly phase frequency equal to gear mesh frequency because the greatest common divisor is 1, as we have 19 teeth on the pinion and 31 on the gear wheel. And this leads to evenly distributed gear contact. Therefore, each gear hunts the gear from each tooth hunts the tooth from the second gear. So each pinion tooth hunts the tooth on the gear wheel. And throughout the lifetime, all the teeth will come in contact. Therefore, with this design, there is lower risk of failure due to enhanced wear or distribution of vibration and so on. Now here in the third video, we will see what is the hunting tooth frequency. Here we have again the design with 18 teeth and 30. And the hunting tooth frequency is the frequency of two specific teeth meshing. So the occurrence of the contact of these teeth with exactly this tooth in the whole lifetime. Now moving forward to some more complex gear pairs, the planetary gears. Here the gear mesh frequency is calculating a bit differently. In the case when we have the stationary ring, the gear mesh frequency is calculated by multiplying the rotational frequency of planet carrier with the number of teeth on the internal gear. In the case when the ring is also rotating, we need to calculate the difference between the rotational frequency of planet carrier and ring gear, and then again multiplying by the number of teeth on the ring gear. For other epicyclics, such as compound planetary stages, Ravignon, Wolfram, or other, some other equations could apply for calculating gear mesh frequency. Now, according to the literature, in planetary gears, we have also some other frequencies which can be divided in two fields. One is local damage case and one is the distributed damage case. The distributed damage case is by definition relative rotating frequency of the faulty gears with respect to the planet carrier. So this means that the frequency which would be measured on the shaft connected to the planet carrier. And the second one is the local damage case, and it's defined as how many times the fault gear tooth meshes with the mating gear per unit of time. If we just look on the equation for the sun gear, the distributed damage case frequency would be calculated by dividing the gear mesh frequency by the number of teeth on the sun, while the local damage case would be higher. It would be higher by the number of planets in this planetary gear. So it would be 3 times as high because the sun is in contact all the time with all 3 of the planet gears. Now we stop. I'll have a short break from the literature and theory, and I will have a live demo on the gear characteristic frequencies inside the Keysoft. I prepared 2 examples. One is for cylindrical gears and one is for 3-gear train. In the cylindrical gears, I will show you the options on how to calculate the gear frequencies, on the tools for finding better design of the gear pair, and also how the gear mesh frequency are represented in graphics and in report. In 3-gear train, I will show you the usage of duty cycle with variable speed. Now I'll jump in the Keysoft version 2023 SP3, which is publicly available. And I'll start my first example. In this example, I have the same gear ratio as I showed you in the videos. So on the pinion, it is 18th, and on the gear, it's 30. To enable the gear mesh frequency calculation, you need to go under the Strength tab, and there you can go and select the gear mesh frequency calculation. Near this selection list, there is a branch which is a specific, which enables us some more specific options for gear mesh frequency. We can calculate the gear mesh frequency by considering the sidebands from the shaft rotational frequency. We can input the number of harmonics at which we are interested. We can choose that the reference speed is from that the operating speed is from reference speed or the speed from load spectrum. We can consider some tolerance range, and we can show some critical speed along ISO horizontal line. And of course, there is 3 possibilities for units. As mentioned, we can output in hertz, in cycle per minute, or we can do an order analysis by normalizing all the values by the reference speed of the reference gear. Now, if I run the calculation and I open the general report, for this case, it's under in the chapter 12, supplementary data, and here chapter 12.2, we have gear mesh frequency at the nominal speed. In the report, there is short summary of the gears, and there is rotational frequency of the pinion and on the gear wheel shaft. For this example, we chose 600 RPM, so to have the easy example to calculate, this reflects to 10 Hertz. Now, multiplying 10 Hertz with 18 teeth on the pinion, we get the gear mesh frequency of 180. Because there is a common divisor between gear wheel and pinion, we have assembly phase frequency of 30, because the greatest common divisor is 6, so 180 divided by 6 is 30. Then in the report, we can find out also some sidebands values. And then there is also values considering the tolerance range. So gear mesh frequency by plus minus the tolerance range. And also at the end, there is a table where we have for 3 harmonic all the fundamental characteristic frequencies and the sidebands. Now, another way to look on the results is to use the graphics. Under graphics evaluation, we have gear mesh frequency. And here we can see that we have the diagram on the y-axis is the frequency, and on the x-axis is the reference speed of the gear. So this plot shows us how the gear mesh frequency or other frequencies are changing with the input speed. Now, in here there are some additional options to help us read this diagram. We can show us the nominal speed, so this is at 10 Hertz. We can see here several lines because we requested the output for 3 harmonics. We can see that the gear mesh frequency is not equal to assembly phase frequency. We can see also the sidebands as we requested them. And we can see the minimal and maximal tolerance range. So for example, we are focused on this area. This is the nominal reference speed plus minus 25%. Now there are two ways to read this graph. So what would be the gear mesh or other frequency at certain reference speed? So for example, at 10 Hertz of rotational frequency of the pinion, we saw that the first harmonic is 180 for the gear mesh frequency. And the second harmonic would be higher, 360, and so on. The second way to read this chart is to go from the y-axis. For example, we have here the eigenvalue from the ISO, and here we can see at which value it interacts. For example, the first harmonic. So if the shaft would rotate at 11 Hertz, we could have some interference. Now in this gear mesh evaluation, there is another plot. It's gear mesh frequency amplitude. However, of course, the amplitudes cannot be calculated. They are usually measured. But on this chart, we can see the distribution of our gear mesh frequency with the sidebands. Now, as mentioned, I would like to show you how to optimize this design. And this can be done by using the fine sizing tool, where we do the fine sizing, and here we have also the output if the gear system is hunting or not. So if the hunting is, that means that each gear is in contact with the other gear, and we don't have the greatest common divisor higher than 1. And here we can see that it outputted quite nice results with slight variation of the gear ratio and of the similar safety factors as we have in our basic design. And if I take this last solution, it will automatically update the calculation. And now if I calculate and go to check the gear mesh frequency in the report, we can see that assembly phase frequency is now equal with the gear meshing frequency, and because the greatest common divisor is 1, we have really low hunting tooth frequencies. Now moving on to our second example is 3 gears in contact in a gear chain. So if I show you how this looks, the system is something like this, compact design. And here we defined several bins for the load spectrum. We have different speed factors ranging from 0.7 of the reference speed to 2 times the reference speed. Therefore, in the gear mesh frequency calculation, we selected that we would like to consider speed in load spectrum, and that we would like to show a reference speed and all the speeds from the load spectrum inside the graphics. If I confirm it and calculate, we can go to evaluation and gear mesh frequencies. Here I would like to emphasize that because we have 3 gears, there are 2 diagrams possible, one for gear pair 1, 2, and one for gear pair 2, 3, because the hunting tooth frequency and assembly phase frequency can be different for these 2 cases. Now, if we take a look, we can here see again with the green line, it's the nominal speed, and all the other lines show us the gear mesh frequency for these different bins. Now in the report, the results are presented in a table, and here we can see that gear mesh frequency for all 5 bins. Now another way to look on this different frequency in respect to different bins is that we enable show only graphic for selected load spectrum bin. And if I recalculate, then the graphic becomes more dynamic, and we can see here for the bin number 1, 2, 3, 4, 5, and so on. Now I will go back to the slides and to continue a bit more with the theory, but from not from gears anymore, but from other machine elements, rolling bearings. So in rolling bearings, we have 5K frequency which are in the interest. We have the rotational frequency of the cage, also named as fundamental train frequency. There is also a rotational frequency of the rolling elements, which is named ball spin frequency. We can have over rolling frequency of inner ring or ball pass frequency of inner ring, and the same is for the outer ring. And we can have also the overrolling frequency of rolling element, also known as ball pass frequency. Now, the first frequency, the fundamental train frequency, is the frequency at which the roller cage enters and exits the load zone, which could be seen here on this animation. So the occurrence of entering this dot in the load zone of the bearing. The calculation of the fundamental train frequency is, of course, again, depending on the rotational frequency, and here in this case is dependent on the rotational frequency of inner ring and outer ring, but also on some geometry parameters such as contact angle, then rolling element diameter and pitch circle diameter. Now, moving forward, the second is the ball spin frequency, is the frequency at which the rolling element enters and exits the zone. So we can see here from this animation, so the occurrence of this dot entering and exiting the load zone. Again, here this frequency is, of course, depending on the rotational frequency of inner and outer ring, but also on the same geometry parameters as shown before. The third one is ball pass frequency of inner ring. So it's the frequency at which the rolling elements pass through a given point of inner track. And this occurrence is calculated by knowing the number of rolling elements in the bearing and fundamental train frequency and the frequency of the inner gear ring. Similarly, the ball pass frequency for outer ring can be calculated. Just here we need to take in consideration the rotational frequency of the outer ring, and we can see it's the occurrence of the rolling elements passing the point on our outer ring. The last but not least frequency is the ball pass frequency. It's similar to ball spin frequency, however, this time it's the frequency that this damage, for example, would touch both inner and outer ring. So it's 2 times the ball spin frequency. Of course, there are some limitations to those equations, and the actual frequency can deviate from them because those equations assume that there is no sliding and that the rolling elements roll over the raceway surface. However, usually usually measured frequency are a bit smaller because there is a few percent, typically around 3% slip in the rolling elements. And of course, all this frequency can be modulated by some other frequency, and therefore the values can also change due to that. Now, I would like to show you the example in KeysSoft, where we have the track transmission shaft. This track transmission shaft is quite complex. It consists of several gears and also different rolling bearings, such as cylindrical, taper roller, and needle roller bearing. And I will again jump into the KeysSoft and change the model. And now I'm in shaft module calculation, where we can see this shaft with several gears and of course several bearings. In the shaft calculation, the bearing frequencies are automatically calculated and they can be found in the general report. The frequency are shown in the last few chapters of the report. So here it would be 15.26, the bearing frequencies. And here we can see that we have all those 5 characteristic frequency of the bearings for the first harmonics, so the base frequency. for all these different bearings in the system. Now, similarly as for the gears, we have the graphic, which can be found by going to graphic, roll and bearing, and then we have bearing frequencies. And here we have these 5 frequencies and also showing the relative speed of the bearing. And via this list, we can change for different bearings in our shaft model. Now, before I mentioned that the frequency are dependent on the rotational frequency of the shaft, or inner and outer ring in the case of bearings, but also on the geometry. And now in Keysoft, we can have the calculation by using proprietary bearing internal geometry, and this is only inside the calculation. This way we get some internal geometry from the manufacturer of the bearing. Now, the user can also use SKF Cloud service or connect with Timken service to gather this exact geometry of the bearing. And now I will show you for some cases this internal geometry data is already precise in the Keysoft, and for other there needs to be some approximation. Now I will calculate without use of the proprietary bearing data to check the difference. And if we compare the reports, this is from the first calculation, so at the beginning and now going to the end, we have without proprietary data, so some approximation was done, and we can see that there can be some difference. While some values are really similar, the other can have slight difference. Now, the summary of this difference is shown in our presentation. So here, this bar chart represents the difference between the use of proprietary data bearing geometry and the approximation. And for some bearings, we can see that we get really similar results, while for others there can be some difference. And I would like to emphasize here that this also depends on the supplier, because some suppliers have their bearing geometry publicly available, and so it's already publicly available inside the Keysoft as well. And this would give us identical results if we would use proprietary data or not. For others, some differences might occur. Now, coming out to the third topic of today's webinar are the other frequencies in the system. So, as mentioned previously, there can be some modulation of the characteristic frequency of gears and bearings, and this is usually due to the shaft rotational frequency. This modulation can also be generated by higher harmonics of the shaft, and the modulation can be above or below characteristic frequencies. So this means that there are some sidebands. If we look on this diagram here, we have Fn, which would be the shaft rotational frequency. We have Fz, the gear mesh frequency, and now the Fz modulated by the first harmonic of the shaft would result to this sideband, and as mentioned, the modulation can be above or below the characteristic frequency, so we get those two sidebands. With second harmonic, we would get those two sidebands, and with the third, we can get those. And usually when it's measured, often it's that the base characteristic frequency could have the highest amplitude and the others may have lower, but this is also depending on some damages or some other parameters inside the gears or bearings. Now we need to look also in the very important frequencies, which are eigenfrequencies or natural frequencies. And those frequencies are the frequency at which the system tends to oscillate in the absence of any driving force. They depend on mass, stiffness, and damping, and they can be they are usually or typically they're constant with the change of input torque and speed, so they can be drawn as horizontal lines. Currently in the Keysoft and Keys design, we can calculate the eigenfrequency of the drivetrain, including several options. We can consider the mesh stiffness according to ISO. We can use the contact analysis for the mesh stiffness, or we can set to infinite or ignored mesh stiffness. Inside the model analysis, which is a part of the Keys design, we can consider also the gyroscopic effect. Now, currently the eigenfrequencies of the transmission cannot be calculated inside the Keysoft. So the transmission here means that the drivetrain would also include the housing and other components, but it can be calculated in some other software which uses the multi-body simulation or finite element software. And now I would like to show you just some example on how this eigenfrequency looks like, the first four eigenfrequency of this simple cylindrical gear pair. And these were calculated by inside the Keysoft. I would like to apologize for this. Microsoft is not responding. Hopefully be back soon. Okay, so we finished with this slide, and then we can go on with also other frequencies in the system, which are often looked are the characteristic frequency of e-motor. They're especially important in EV drives because the higher orders can be close to the gear mesh frequency. Typically relevant components of the electric motor are pole pair number, pole number, slot number, which is usually the multiplies of pole number. Then there is torque ripple and cogging torque. Cogging torque is the interaction between the permanent magnets in the rotor and the slot of the stator. Due to the change in stiffness, there can be also some other characteristic frequencies inside the gears, which are connected to the bolt holes of the gear bodies. This is typically for bevel gears, but also due to some lightweight design in gear body and some other modification to the gear body. Another topic that needs to be covered when we speak about the drivetrain frequency is the ghost frequencies. I need to emphasize that the ghost frequency are not related to the gear mesh frequency in the current design, but they are usually high frequency and create disturbing noise. They are typically caused by the manufacturing, such as honing and generation grinding, and this could be connected to the, for example, index wheel on the grinding machine, which is typically has quite a lot of gear teeth, so around 190 or even 200, and then we have some grinding wheel which operates on the workpiece, and then due to some manufacturing deviation or some other, we could get some specific pattern on the gear. Now, according to Gleason, there is the way to identify this ghost frequency, but it requires that the single gear is measured in profile, lead, and pitch measurements, and also this needs to be carried on all teeth. Gleason offers the advanced waviness analysis to help investigate these ghost frequencies, and also the ghost frequencies can be investigated by acceleration sensors or the eigen modes of the workpiece and tools and dressers. So currently, this ghost frequency cannot be calculated in Keysoft, but the knowledge of all the other frequencies help us identify the ghost frequency. Now, here is an example of how this profile waviness analysis from Gleason works. So we have measurement of profile deviations, so these color lines in all teeth in one section. Then we merge them and measure the profiles according to the tooth mesh. And then we remove the overlapping areas. So this it results in this enveloping black line. Then we can use the Fourier analysis to transfer the black line results in the frequency domain. And here we can see some increase in amplitude, but this is connected to the first, second, third, and fourth harmonic of the gear mesh. And the other amplitude that comes out are the ghost frequencies. So these harmonics could be calculated by the Keysoft, and the rest which stands out could be linked to the ghost orders. Inside gear, which is usually a part of some transmission inside gearboxes, we can have also the gear rattle. This is typically for gear pairs at idle speed, and there is no distinct frequency. And the gear rattle is when the gears are vibrating within their backlash range. And of course, this gear rattle is impacted by the gear geometry. So the larger the backlash range, the higher probability of the gear rattle is. Then it's also connected to operating parameters, materials, and also the lubrication. And for lubrication, it's not only the viscosity which is important, but also the fluid film inside the transmission. The other characteristic frequencies are also possible from manufacturing, such as nicks and burrs, and in case of polymer gears, there can be also some squealing from the material. Now, according to the ISO standard for cylindrical gearbacks, so 6336, or ISO for bevel gear 10300, there are 4 running ranges. For the resonance speed, there can be a subcritical range, main resonance range, and intermediate resonance, and supercritical. Now, with some special design where there's some modification on the tooth, or when we have the gears with really precisely made, so in the tolerance class below 5, we can also operate in the main resonance. Else we should avoid it. And this resonance, according to the standard, is dependent on the relative mass of the gear pair and also on the mean value of the mesh stiffness per unit of face width, and of course on the number of teeth on the pinion. And this gear resonance speed could be shown as horizontal line inside the gear frequency calculation, and also I'll show later in Key's design. Now, to summarize the importance of the knowledge of this inside the design phase is we should avoid the resonance. So this means we should avoid the operation of the transmission where the characteristic frequency interacts the natural frequencies. Then we should also avoid having similar characteristic frequencies of different components. So example, if we have 2 gear pairs, we should avoid having similar gear mesh frequency. In the design phase, we should cover and check the tolerance range, which could be defined in relative, in absolute values, and also in order to filter out the critical frequencies. In case of the designing of EVA transmission, gear mesh frequency and higher harmonics of E-motor are typically critical, while the bearing frequencies are usually much lower. And as shown in the first live demo example, we should avoid having a common divisor of gear teeth higher than 1, so we should strive to have the hunting tooth, so that each tooth is in contact with another tooth during the meshing. This covers the first part where the characteristic frequencies are important, and the second one is in the already designed gearbox, where we do a condition monitoring. So we do a vibration analysis by capturing the raw signals which are emitted from the machines using different devices such as direct voltage output. We can use microphones, but often the accelerometers are used. And then there are different processing techniques that can be used for further analysis and to find the frequencies inside the spectrum. So typically the amplitude time is measured, and then we would need to transfer to the frequency domain to see at which characteristic frequency we have increase in amplitude. With this analysis, we can typically find for different defects in gears bearings, but also some bent shafts, some misalignment, resonance, and so on. Now, according to the literature, we can have, by knowing the gear mesh frequency and having the measured signal, we can identify eccentric gear or bent shaft, is that we have the modulation in the gear mesh frequency and the sidebands of the eccentric gears. Then we can have tooth wear or broken tooth, where we would see amplitude in the natural frequencies, but also in gear mesh frequencies. Then for the increase in backlash, typically it's that we have high amplitude in the first gear mesh frequency and lower amplitude in the other. And for example, for gear misalignment, we typically have higher amplitudes in the second harmonic with some significant sidebands around it. Similarly, for bearings, knowing the characteristic frequency and having the measurement, we can identify the outer race defect or the inner race defect. For inner race defect, sidebands are usually seen because the inner race is closer to the shaft. Then we can have some rolling element defects when we have high amplitude at ball spin frequencies, and also some sidebands around it. And of course, also for bearing cage defect, we can see some increase of amplitude in this fundamental train frequency. Now, I would like just to emphasize that when performing these measurements, it's typically that all measurements needs to be done at the constant speed, so that when we do a comparison, we don't see the influence on the speed of it, as we saw that all frequency are speed dependent. Now, there is another module coming out from Keysoft, which will be released next year. It's the Keys Design. The Keys Design collects and enables the combination of shaft, gear calculation, and other mechanical elements in it. And also the frequency analysis enables the user to input its own frequencies. And for this, I prepared two examples, which we will now see. The first example is the industrial gearbox, and the second example is EV gearbox with the housing and also e-motor characteristic frequencies. Now we jump to the software, and this is not publicly yet available as it's part of 2024 release. So I opened this industrial gearbox, where we have the planetary gear set, which transmits the load to the cylindrical gear pair, and then it goes out through the bevel gear pair. This is how it looks in the sketcher, and if we go to the 3D viewer, we can see from this side. And I modified slightly this industrial gearbox by adding another boundary on the ring gear. This means that on the boundary, that on the ring gear, another boundary condition can be added, such as that the rotational frequency of the ring can be modified could be 0 or something else. To do this, I used the load spectrum inside it, and the first load spectrum is when the ring would be fixed, and the second is if we would add some rotation to it. In KISS design, the frequency analysis is a part of special calculation, which can be accessed through calculation frequencies. And inside of this, we have several options. The first options are to select only the frequencies from the to choose only the frequencies which would like to be analyzed for gears, bearing, and shaft. So on plus button, there is a possibility to investigate only gear mesh frequencies or other frequencies, and to consider the stages, so all three or only one, and so on. Similarly, it's also for the bearings and shafts. And then there is the reference speed definition. It could be from boundary conditions, so input, output, and ring as we have defined, or from the shafts. Then there is a speed range, which we are interested for the analysis, and there is also the possibility to define the number of harmonics. Now, as mentioned, the sidebands are really important. So in this frequency analysis, the sidebands from the shaft rotational frequencies can be considered, and we can choose only one shaft or all of them, and we can also add the harmonics of that shaft that modulates the characteristic frequencies. We can again here consider operating speed tolerance range in a percentage or in the absolute value. We can consider gear's critical speed according to the ISO. We can consider the eigen results from model analysis and compare them to the characteristic frequencies. We can also consider frequencies from other components, which will be shown in the next example, and we can output the similar frequencies. And equal to the gear calculation frequency module, we can have here units in Hertz cycle per minute or normalized, so for the order analysis. Now, if I calculate this, here in the results, it's just a brief summary of the boundary conditions and the input reference speed and the 3 gear meshing frequencies, so one for each pair. Now, the result for the frequency analysis in KISS design, it's a part of a special report. For this, the user needs to be on this tab, because you can see here this icon, and then when the report is open, we have the special report for frequency analysis. Again, some general input. Then we have the shaft rotational frequencies, the gear frequencies for 3 harmonics as they were defined in the settings. And then we have bearing frequencies for each of the bearings. And then we have also some gear frequency modulated by the sidebands. So this is the base frequency and modulated by the -1 rotational frequency of shaft 1, and here is -2 times the rotational frequency of shaft 1, and here is the plus values. At the end, we can also output some similar frequencies. Of course, now due to the bearing analysis, we have a lot of similar frequencies, and when we are interested only in gears, we can see here that we have some similar frequency of the first harmonic of pair Z1, Z2 with the second harmonic of Z3, Z4. Now, also in KISS design, we have 2 possibilities. One is the frequency domain and one is the amplitude domain. In frequency domain, we can see here this typically graphic for the analysis. So again, on y-axis is the frequencies, and here we have the change of the reference speed. Now, this plot is quite crowded because we have 2 sidebands on each harmonic. Now, if we hide them, we can see a bit better, but this graphic enables also the dynamic analysis, so we can start focusing on the first harmonic. We see the gear mesh frequency of all three pairs, and now if we check on the second harmonic, here we can see that there is some really similar frequencies. So the first harmonic of the blue pair, which is Z1, Z2, is similar to the third harmonic of the second gear pair, and this was also seen here in the report. Now moving forward with our last example is EV transmission. This EV transmission consists of the input shaft which leads to the first cylindrical gear pair, and then we have the second cylindrical gear pair, and then at the end there is some compact differential. In the 3D view, this would look like something like this. As mentioned, we also inputted the step model of the housing and of the motor. And here, this is the first gear pair and the second gear pair, and then a differential. Now, for the frequency analysis, I would first like to show you the second graphic where we show the gear frequencies and all the bearing frequencies to emphasize that the bearing frequencies are truly much lower than the gear mesh frequencies. Now, if I go step by step, here the first two, this is for the first gear mesh frequency and the gear mesh frequency of the second part. But if we check the higher harmonics, this difference becomes even more prominent. Now, as mentioned, we have the possibilities to input some user input frequencies. And for example, we have some parameters from the electric motor. We have the pole number, which is 3 times the order of the input shaft. We have the torque ripple, which is 18th time the input shaft. And we have the slot number, which is 72 times the input shaft. And here the frequency are automatically calculated. And then there is a possibility to also input the absolute value. For example, this housing and drivetrain, this whole transmission was studied in FEM, and it output the first eigenfrequency at this value. And with input of this, we can run calculation and go to graphics, frequency domain. And we can see that this transmission eigenfrequency intersects with the gear mesh frequencies. Now for this example, I'm interested only on gear mesh frequency for both pairs and not for the differential. And with the showing of the nominal frequency, we can see, okay, here is the nominal speed and the transmission frequency, so the transmission eigenfrequency is quite close to the nominal speed. This can be easily seen also in the report, where we have the user input frequencies, and then at which value there is the resonance between each component. So for this case, we look here on the fourth resonance. So the first harmonic, so the gear mesh frequency from pair Z3, Z4 would be in the resonance at the nominal speed of 232, which is quite similar to the input speed. Okay, this is what I wanted to show you in KEYS design. And now I would like to go back to slides to conclude my presentation. So we saw that the characteristic frequencies are an important topic in both design phase and also later on in the predictive maintenance. Gear frequency are dependent on the rotational frequency, on the gear teeth, and on the composition of the system, while the bearing frequencies are dependent on the rotational frequencies of inner and outer ring, and also on the bearing geometry data. In the Keysoft, it enables the calculation of the characteristic frequency in gear module and in shaft module for the bearings, while the KEYS design can collect all these characteristic frequency for the whole drivetrain and is a valuable tool for analyzing the intersecting and similar frequency, which helps us in the design phase. Thank you for your attention in today's webinar. I think you can find the handouts, so this presentation can be downloaded. Now I think, I spoke for an hour, but I'm ready to take one or two questions if there are any. So there is a question on how to calculate the harmonics to subsequently incorporate them into the frequency calculation. So in KEYS design, it enables us to have a user input frequency, and this way the user can add the frequency which he previously calculated them. So for the calculation of the bearing frequency in Keysoft module, it is necessary to have the shaft module, and in the shaft module, it's automatically the frequencies of bearings are calculated. So I think now we are quite past our 1 hour time, and with this I would like to conclude, and for the questions which I did not answer now, I will answer them via email. If you have any additional questions, you can send us email on info@keysoft.com. Thank you for your attention. Bye.